So good Wednesday afternoon, everyone. Welcome to lecture 2 in mathematics for construction. We're continuing from fractions. We did a lot of fractions in lecture 1. Today we want to talk a little bit about number theory and how to use basic number theory to find certain popular things about numbers. Okay, so we review. We talk about an integer. Integer is a whole number, right? There's no fractional parts. So fractions are not integers unless the fractions are whole numbers, right? Like a half and a quarter, those are not integers. Those are vulgar fractions, right? No fractional parts is what makes a number integer. So examples, -4, 0, 3. Prime integer is an integer which is not equal to 1. The only factors are itself and 1. Examples of prime numbers is 2, 7, 11, 29. Composite numbers are numbers that are not prime. So a number is either prime or composite. Okay, that's a review. Prime factorization is about splitting up a number into a product of prime numbers. Okay, so the idea is that integer is either prime or is a product of prime numbers. Composite numbers are product of prime numbers. And this result is stated more complicated and more formally in something called the fundamental theorem of arithmetic. You could Google these things on Wikipedia, could talk about it, right? So example here we have 11 as a prime number, so just represent it as 11. But 60 is a composite number, okay? So 60 is, say, 2 by 30. But 30 is also a composite number, so you can split up 2 and 30 into 2 by 15. And then 15 is also a composite number. So 15 is 3 by 5. And there you go. 60 is a product of prime numbers, okay? All these numbers here are prime. 2, 3, and 5, they are prime numbers. So this is the importance that prime numbers play in mathematics. They are the building blocks of the integers. Any integer is composed of prime number if it's not a prime number itself, okay? So that's really what prime factorization is there in a nutshell. So after prime factorization, we want to talk about factors and multiples, okay? So what is a factor and what is a multiple? These things are defined for integers, okay? Whole numbers. So A, capital A is a factor of integer B if B is equal to A times something, okay? So basically 1 is a factor of everything and every number is a factor of itself because we could multiply something by the factor to get the original number, okay? 3 is not a factor of 5. We can't multiply another integer by 3 to get 5, okay? So that is the idea of factor. An example there, 3 is a factor of 12 because 12 is something by 3, in this case 4. Multiples are integers as well. This is defined for integers. A multiple of our integer y is some integer x that is y times something, okay? So a multiple is bigger than or equal to the number, the multiple of a number. So example, 15 is a multiple of 5, right? Because 15 is 5 by something. So multiples and factors go hand in hand. A multiple of some number would mean that the number is a factor of the multiple, you know? HCF and LCM. Highest common factor is also called greatest common divisor, or GCD. Divisor is a synonym for factor, okay? So if you want to find the HCF of 2 more integers, you have to find a number that is common to all of them, which is also a factor of all of them, okay? And the same idea exists with multiples, right? Lowest common multiple is a common multiple, is a multiple of all the numbers that is common to all of them, but we want the lowest one, okay? So let's see how to find HCF and LCM. So for to find the HCF and LCM of 30 and 45, what we do is we find the prime factorization of each number. And this tends to be easy sometimes, or it may be difficult. The bigger the number it is, the more difficult it is be. So 30, let's find the prime factorization of 30. And this is a very easy technique that works well for fairly small numbers, like 2-digit numbers and 3-digit numbers. After you cross 3-digit numbers, it starts to get difficult to use this method. Okay. So 30 is what? 30 is 3 by 10. And since 10 is not a prime number, we can split it up even further. This is 3 by 2 by 5. Okay. So right, it has 2 by 3 by 5. What about 45? 45 is 5 by 9. 5 nines are 45. This is 5 by 3 by 3. Can we write it in order? By 3. Okay. So after you do this now, you write down the numbers in a table, a tabular fashion, right? So 30 is, we have a 2 here by a 3 by, I say a 5. 45 is 3 by 3 by 5. So we put a 3 here by, put a 3 by and 5. So the idea is we write the factors, the prime factors in a table, but we align the columns in terms of the factors, right? So this 3 here for 45, this goes together with this 3 here. Okay. So this 3 could change the color to pink and bold it. Same thing here. So the 3 is common. What you want to do, you want to make sure you use up as much factors that you have in common. Okay. Also, the 5 is common to both 30 and 45. So this 5 here is common. "45 has a 3, has 2 3s in it, but only one of the 3 is used up. And then for the HCF, we write the numbers that are common. So the HCF will be 3 multiplied by the common number 5, right? Equals 15. That's how you find the LCM. And then, sorry, the HCF. The LCM, we take the numbers, all the numbers, right? And we multiply them here. So we don't include 2 5s, we only include 1 because they used up. So 2 3s are 6, 6 5s are 30. This is 90, okay? Which makes sense. It's really 45 by 2. So that is how you find the HCF and the LCF. You try to use up the numbers in the table. So if you have a 3 and a 3, you combine them, but you can't combine the second 3 with anything else unless you have a 3 on top here as well. These 5s combine into 1. This is how you find HCF and LCM. You try to use the factors as much as possible. You don't want to overuse them, otherwise the number will be bigger or smaller than the case may be. Okay, so this is a general idea to find HCF and LCM. If we give you one to do now, the same way. Okay, so use the same technique here to find the HCF and LCM of 60 and 75. So let's start by doing the prime factorization of 60. Okay, 60 ends in 0, so it's a multiple of 10 or 2, right? So this is 10 by 6, essentially, right? And you can split up the 10 and the 6. 10 is 2 by 5, and the 6 is 2 by 3. Okay, so you can write that 2 by 2 by 3 by 5. Okay, so you put it here. Let's do 75 first. 75 is 5 by something, right? So this is 5 by, I think, 15 is what it is, right? And we can split up 15 some more. 15 is 3 by 5. So we end up getting 3 by 5 by 5. Okay. Now you fill it in the table. I put 2 by 2 by 3. So 35 here now. So 2 by 2 by 3 by 5. That's what I have here. Then this is 3 by 5 by 5. So 75 is 3 by 5 by 5. Okay. So what we see we try to see what we could use up, right? So this 3, the first 3 in 75 could go under this 3. The first 5 could go under this 5. Now we use up 3s and 5s. So if we have an extra 5, it has to be by itself. So we try to combine the columns into one, okay? So the HCF would be the things that were highlighted in common, okay? So the HCF will have a 3 and it will have a 5 in it. So 3 by 5 is 15. Right? The LCM will have a representative from each column. So we'll have a 2, we'll have a 2 here, we'll have 1, 3 here, we'll have a 5, and it will have a 5. So 5 5s are 25, 25 by 4, 2 2s are 4, 25 by 4 is 100, 100 by 3 is 300. Okay, so that is the HCF and the LCM there. So we try some examples, right? Let's try 210 and 315. Okay. So I have 3-digit numbers now. That's the next example, right? HCF and LCM of 210 and 315. You don't really need a calculator for this. You could do the prime factorization of both numbers first, split it up into primes, right? So let's see how we could solve this problem here. We'll try the prime factorization of 210. Now 210, it, it, it ends in 0. So we know it's a multiple of 2 and 5, which is 10, right? So this is 2 by 5 by 210 is 21 by 10. So 2 by 5 is 10 by 21. So, we can represent this as that, like this, 10 by 21, right? And 10 is 2 by 5, and the 21 is 3 by 7. So we write it in order. We could say this is 2 by 3 by 5 by 7. Okay, that's the 210. 315 now. That ends in 5. So we know it's a multiple of 5. So this is 5 by something, right? 5 into 31, 6 5s are 30, and 1, 5 into 15, 3, okay? 63 is not a prime number because the sum of the digits is a multiple of 3. 6 and 3 is 9. 9 is a multiple of 3. So this 3 can divide that. So this is 5 by 63 divided by 3. So this is 3 by 21, right? So this is 5 by 3 by 3 by 7. And we could represent it in ascending order of numbers like that. So for 210, I will do 2 by 3 by 5 by 7. 315 now. I have 2 3s, so I will put 1 3 under this column here, but I have a leftover 3 that I can't put under any other column. I only have 1 3 column from the 210. So this 3 kind of escape a little bit. Then I have a 5. So I could say, well, I'll put this 5 under the 5 column, and I'll put this 7 under the 7 column. All right. Now the HCF would be the columns that have numbers in common. So definitely the 5. And also the 7. So you see the 3, there's a 1 3 in common, there's a 5 in common, there's a 7 in common. So the HCF will be 3 by 5 by 7. So what's 3 by 5 by 7? 3 5s are 15, and 7 sets of 15. Okay. 4 sets of 15 is 60. Right, so that's a little bit less than 120. That's 105. Now the LCM is you multiply all the representatives of each column. So we have a 2 column, we have a 3 column, we have another 3 column, but it only has 1 3 in common. We have a 5 and we have a 7. Now this is a big number, okay? The 25, we could worry about that after. We have 3 by 7 is 21, and 21 by 3 is 63, and 63 by 10 is 630. Okay, so that is the LCM there. and the HCF. So we want to talk about something called indices, okay? Powers or exponents, right? So these are synonyms, okay? So we're going to start our discussion with numbers and then we'll move towards letters eventually, right? So when we write this here, 2, and to the top right, we write a small 3. We say that's 2 to the power 3. Now, power is another synonym for power is index. So we say this is a 2 to the index 3, or 2 to the power 3, or 2 to the exponent 3. Okay? Index, power, exponent, all those are synonyms. Okay? The 2, right, in black is called the base, and the 3 in red is called the power or the index or the exponent, right, as the case may be. So an integer power n, if the power is an integer, okay, it means we multiply the base by itself n times. So 2 to the power 3 means 2 by itself 3 times, 2 by 2 by 2, which is equal to 8. Okay, 2 2s are 4 and 4 2s are 8. So using that definition for integer power, work out what these values would be for me. What is 2 to the 4? What is 3 cubed? What is 5 to the power 4? You don't need a calculator. Right? Try and work it out without a calculator. So 2 to the 4 is not 2 multiplied by 4. It's 2 multiplied by itself 4 times. Okay? So you say 2 times 2 times 2 times, right? So 2 multiplied by itself 4 times. So 2 by 2 is 4, 4 2s are 8, 8 2s are 16, okay? That's the idea, right? So do the same thing for the other two, in case people were confused as to why 2 to the power 4 is not 8, right? You don't multiply the two numbers.
All right, so get you.
So 3 cubed, what is 3 cubed? 3 times 3 times 3. 3 3s are 9, 9 3s are 27. Okay, so that's the answer for that. 5 to the power 4, number starts getting a little bit big. It's 5 by itself 4 times. So 5 5s are 25, and it's 25 by 25, it's 25 squared. That's 625. Okay, if you want to know how I knew that, is a familiar number to me. 5 to the power 4, 625. So that's it. So let's look at some basic laws of indices. Right? Consider the following: 2 cubed multiplied by 2 to the power 4. Right? So let's write what this means. Okay, let's really write what it means. In the sense that we will rewrite the question but put it in brackets. Okay, so let me rewrite the question and put the two pieces in brackets, right? So 2 cubed, I'm going to compute that separately, and 2 to the power 4, I'm going to compute that separately. Well, what's 2 cubed? Right? 2 cubed is 2 by itself. We're not expanding it yet, right? We're not giving a final answer. 2 cubed is 2, okay? And 2 to the power 4 is just that, okay? So 2 cubed, which is the one on the left, is 2 by itself 3 times. And 2 4 2 to the power 4 is 2 by itself 4 times. The question is, how much 2's do I end up with in total? I have 1, 2, 3, 4, 5, 6, 7. That's 7 sets of 2's in all, right? So I can represent that now without brackets as 7 sets of 2's. It might be hard to see 1, 2, 3, 4, 5, 6, 7. 7 of them in all, right? But that is, we know that is 2 to the power 7, right? But instead of expanding this out, there was an easier way we could have find that out, you know. I know, well, okay, I have 3 2's here and 4 here, so 3 plus 4 is 7. So what it really ended up doing is writing 2 to the power and 3 plus 4, okay? So instead of doing all the work of multiplying it out, you could realize that, well, I just need to add the indices. This is 2 to the 3 and 2 to the 4. Once it's the same base, you could just add the indices and you don't need to do all of this work here. So just say 2, 3 to the 4. 3 plus 4 equals 7, right? And we could generalize this. We could say x to the p multiplied by x to the q. Once the bases are the same, we just add the indices, x to the power p plus q. Okay. So multiplication of two terms, which has the same base raised to a different power, what we do is we add the indices. This is the first rule here. We'll summarize them in the end. Okay. So let me duplicate this. Now consider the following. We have a different problem here. What if I have 2 to the power 7 divided by 2 to the power 4? What is this equal to? Okay. Well, let's expand it out. First, let's write it as a fraction. Okay, this is a fraction. The term on the left is the numerator, the term on the right is the denominator. And we could possibly split this up. 2 to the 7, that's a lot of 2's. That's 7 2's, right? So in the numerator, I have 1, 2, 3, 4, 5, 6, 7 2's. And the denominator, I have 1, 2, 3, 4 2's, okay? And we don't need to multiply this out and get an answer and then divide, right? The idea is these 2's will cancel, okay? For example, this 2 down here could cancel with a 2 up here. These 2's cancel, okay? And we could keep canceling, right? We'll cancel another one like this here. And I have 2 more down here that could cancel with 2 more up here. I have more 2's in the numerator than the denominator. So I could keep canceling. So 3 2's below cancel, 3 2's above. And I have 1 more 2 that could cancel in the bottom. So 4 of the 2's from the bottom canceled 4 of the 2's on top. Leaving me with what though? What am I left with? I have no denominator. I just have a numerator now. So I have 2 by itself. 3 times. Okay, this is 2. We know how to write this. We can write this as 2 to the power 3. But I didn't need to do all this mathematics and canceling here to figure this out, right? I could have just looked at the indices. I know 237 is 7 of them and 234 is 4 of them. So 4 of them will be taken away from 7. So this is actually 2 to the power, and I could say 7 minus 4. Okay, 7 minus 4 is 3. So when you divide in 2 terms with the same base but different powers, we subtract the powers. Okay, I could generalize this. Generalize this now. X to the p divided by x to the q, we subtract the powers. You subtract the second one from the first one. We say first minus second. This is when you're dividing and it's the same base but different powers. Up here is multiplying, is the same base but different powers. So you add the powers. But when you're dividing, you subtract the powers. Right? So try these 2 questions here as an application of these 2 rules here. Try these questions here just to see if you understand it so far before we move on. So once you apply the rules, right, is basically addition and subtraction of the powers, right? So this is 3 to the power, and we have to add the 4 and the 5, so you get 9, right? And you don't need to evaluate what this really is. 3 to the power 9 is a kind of big number, right? We can leave it like that for now. Here we divide in, so we need to subtract the indices. So this is 4 to the power, and I should probably put the work in, right? This is 8 minus 6. This is 4 to the power 8 minus 6 is 2. And for small one like this, you could put the answer 16. This one here, let me put the work in. This is 3, 4 plus 5, 3 to the power 9. Okay, so that's the answer there with this. So let's move on. Let's see. Let's consider something else now. What if I have two to the power 3 all to the power 4, right? So I have this new situation now where before I had 2 things, right? Before I was either multiplying 2 things or I was dividing 2 things, right? Now I have a 1 thing alone, 1 base to a power, and I'm raising it to another power. Let's use the definition of what the power 4 is, right? What's the power 4? 4 means we have the thing by itself 4 times, right? So this is the definition of what it means to raise something to the power 4. But the thing we are raising to the power 4 is itself a power. So this 2q by 2q by 2q by 2q. Now, from the first rule, when we multiply 2 things with the same base, we add the powers. So basically, these first 2 things here, right? This is equal to the first 2. If we combine them, we get 2 to the power 3 plus 3, right? I get this here. The first 2 items, I combine them, 2 to the power 3 plus 3, multiply by, and I have these other 2 terms here on the right. So I could probably put brackets around this. Oops. Like that. Now this is 2 to the power 6. Right? It's 2 to the power 6 by 2, 3 by 2, 3. Now I could combine these two terms now. 2 to the 6 by 2 cubed. I could add it again. I could say this is 6 plus 3. Right? If I combine these two terms here, I get 2 to the 6 plus 3, which is 9. So now I have 2 to the 9 by 2 cubed. And then, yeah, I keep applying the first rule again and again. This is, you have to add 9 and 3. But I mean, if you think about it, right? I have 4 sets of 3 twos. That's 12 twos in all. So that makes sense. Because 4 by 3, 4 by 3, which is 3 by 4 is 12, right? So this rule says that, well, when you have one thing which is raised to a power, and then you're raising that to another power, you multiply the indices. So you multiply 3 by 4 to get 12. Notice you're not adding 3 to 4 to get 7. This is 4 sets of 3 sets of twos. 4 sets, and each set has 3 in it. That's 12 in all. Multiplication is a shorthand for repeated addition. Instead of adding something 4 times, I could just multiply by 4. So each one of these buckets, I have 3 twos, and I have 4 sets of them. Well, that's 12 in all. 3 by 4 is 12. Multiplication is shorthand for addition. So really what this 12 is here, this really was 2 to the power 3. We multiply the indices, okay? 3 by 4. So if we had to generalize, we could say if I have some number or letter x to the p and I raise that to the power q, I multiply the indices. So you have a single base to a power, and then you raise that to another power. We have to multiply the exponents and keep the base, okay? So let's try an example. So try working out these problems here. You don't need to calculate the final answer, but tell me what is the actual which is the actual power. And bonus for this one, this answer here is 2 to some power, but what is the power? All right, this is a trickier question. This one is easy to do, more or less, But look at this one here. I have 4 squared all to the power of 4, but I'm telling you the answer, represent your answer as 2 to some power. So think about this carefully. This one is a little bit different. So you could just apply the rule straightforward, right? We know from the rule above, when you have something to a power and then you're raising that to another power, you keep the base, right? You keep the base and you just multiply the indices. 3 by 2 is 6, okay? And I'm not too interested what this number is, but is, 27 squared, right? Just a couple hundred, right? Not so important what it is. But this one now, this one is a little bit tricky, okay? Let's, first of all, let's just, we know it's 2 to something, right? But we will worry about that after. This is 4 to the power, and we multiply the indices. 4 by 2 is 8, right? So the answer is really 4 to the power 8. But 4 to the power 8, I'm saying that is 2 to some power. Now how you would do this? This is how you would do this. 4 to the power 8, you rewrite it, okay? In brackets, 4 is really 2 squared. See that? 4 to the power 8 is really 2 squared to the power 8. And now you use the rule again. What is 2 by 8? 2 by 8, 16. Okay, that is how you do this one. So as we head towards subjects like advanced algebra and quadratics and calculus and these things, powers play a big role in that. And you have to understand how powers work and little tricks like this here, how to see things as a power, how to see a number as a power of another number. Like 9 is really 3 squared, okay? Something like 25, that's 5 squared. And sometimes you have to notice cubes as well, like 27 is 3 cubed, 125 is 5 cubed, right? 8 is 2 cubed, right? These things you would have to keep in your mind as we move to more advanced mathematics that requires more sophisticated techniques. So I want to ask you a question now. What's the value of this? I'm gonna type it out for you. Oops. What do you think this is? What is 3 to the power 0? I mean, that makes sense what it is, but what do you all know it's supposed to be from your math education before? You have a finite number raised to the power 0. What is the answer? Anybody knows? Right, so Renanson is correct. The answer is not 0, it's 1. Okay. So any non-zero number to the power 0 is 1. Okay. Now, here's the next question. What is this? 5 to the power 1. What is that? Anybody? Make a guess. 5 to the power 1 is what number? Is it 0? Is it 1? Is it 10? What is it? Feel like it's a trick question. Right, so Andrea has the right answer there. 5 to the power 1 is just 5. Okay. So any non-zero number to the power 1 is the number itself. And let's do an experimentation exercise now. Oops. What is this equal to? 2 to the power 4 divided by 2 to the power 7. Right? I could even write it as 4 2 to the power 4 divided by 2 to the 7. This is a fraction. Okay. Let's consider what this means. We could use the formula up here. When we divide, we just subtract the powers. So we could say, well, you know, this, I know using the rule, this is 2 to the power, what? 4 minus 7. Right? This is 2 to the power. But 4 minus 7 is -3. So this is odd. What do you mean by 2 to the power -3? What is this really? So let's see what this really is. 2 to the power 4 is 2 by itself 4 times. And 2 to the power 7 is 2 by itself 7 times. Okay? And we know all these, there's an excess of 2's in the denominator. So all the 2's in the numerator cancel with all the 2's in the denominator. So where will end up with? Right? All the 2's in the numerator cancel out. So this is what I end up with. These 4 2's above cancel with these 4 2's below. What is the fraction that I end up with? Well, the numerator is 1. And the denominator is just, oops, 2. It's 2 by itself 3 times. 2 by itself 3 times is a fraction 1 over 2 to the power 3. And that is what negative power means. A negative integer power, it means 1 over the positive power. Okay? This example shows you where it comes from, why it is the way it is. So 2 to the power -3 is 1 over 2 to the power 3. This example shows you how it works. Right? So we could summarize and say, you know, generalizing what we could say here. Generalizing, we could say x to the power minus n is a fraction. is 1 over the power, 1 over x to the power n. Okay. And now that you understand that, we could give a summary of all the rules we did for today. And there's a basic laws of indices here. So let x be a non-zero base. X is not 0, right? X is some finite non-zero number like 2, 3, 4, 5, that kind of thing. For non-zero x, x to the power 1 is x to the minus p is 1 over x to the p is some integer power. X to the p by x to the q, we add the indices. X to the p divided by x to the q, we subtract the indices. And then we have one term, x to the p, being raised to the power q, we multiply the indices. These are the rules of indices here. And we just went through why they are the way they are. We went through examples, right? So you kind of get convinced of why these things are, how they work, right? So good.